This is Lab 21, and this lab is on boosting, and this is associated, of course, with Lecture 21 on the same topic. So this lab is just going to run through some simple boosting. There are a couple different packages in R to do boosting. The one I'm going to work with is GBM. But first, let's load up our data. So let's work with spam base again. This is this spam data, and again, you can get it from the UCI UCI repository. We could also get it. It's in a couple packages, in particular base reg. Don't really need to worry about that. Is it's a package that has it, and we'll copy some of our code from last time. So it's going to load up our data, and we're just going to rename the column names as last time. We want to make sure that our column names work out well. Okay, and to do boosting, we are going to use the GBM package, and you probably have to install it. GBM. So I'm called library GBM, and GBM stands for gradient boosted model, or something along those lines. GB is gradient boosting, and the main function for the GBM package is the function GBM, which is generalized boosted. I guess generalized for boosted regression modeling. Fine, or GBM. This word regression, you should be careful here. It's the regression in the same way that logistic regression is regression, in so much as it's classification, actually. So it can do both what we would call a regression problem or a classification problem, or anything in between, but it's kind of a general boosting package. So there are some other packages out there, and we can read our little help description on the GBM package, and it tells us about all of our different things. So formula. Distribution will leave as Bernoulli. This distribution function or argument really specifies that loss function. We'll leave it as Bernoulli for binary classification. Data number of trees is what we're calling B in the lecture. So just like number of trees in a random forest, number of trees, they start with 100 here, but you can change that. Interaction depth is basically the size of the trees. So each of the base learners, typically, we leave interaction depth at 1, where you have a stump as a base learner, but you can change it to like 5, and this would be, you would have a 5 split tree, for example. The reason it's called interaction depth is because if you have like 1 split, you have 1 variable. If you have 2 splits, you can have you can kind of encode the interaction between 2 variables. 4 splits encode a 4-way interaction, and in some way that's true for a tree. And it has some other stuff related to cross-validation, which you can have internally do, and it won't in this case, but it does has a lot of nice bells and whistles associated with it. The only other real important one is shrinkage. So it turns out, and we kind of gloss over this in the lecture, is that oftentimes you want to control overfitting. So a couple ways you can control overfitting. One is the number of trees. You don't have that too big. You don't totally overfit. And the other one is the shrinkage. So it turns out that one way you can control overfitting is you can at each iteration, instead of just adding on, instead of just fitting a new model, you actually, when you do the sum, you actually shrink them as you go along. So you lessen the influence as you go along, and that kind of naturally kind of peters out so that you can't overfit as easily by kind of downweighting for trees further into the fitting routine, right? So it's not like a random forest where all trees are kind of equal. In a boosted model, the order of them matters. And as you get further out, you have the potential to be overfitting, and so if you kind of downweight those, so what they do is they basically raise it to some power. Is how that shrinkage works. So it's a tuning parameter that you can use to help hopefully control overfitting. So the dimension of our original data is 4,600 about. We have our 58 covariates. We can split this, of course, into training and testing. So let's just draw some training. Let's say do a 50-50 split. So this would be a training subset. Train subset. All right, and if we want our testing subset, or, well, we could just define our training data, which is just grab off those training, and we can maybe call it validate. It's our validation data, which is the non-training indices. Okay, so if we look at this, we have about 2,300 in each. So we can fit our model now, fit on our training data, and we can fit it using our GBM function. And of course, the variable we want to predict is spam, and we can predict it from everything else. That's our little formula. Our data is going to be the training data, although by default this is true. We'll just leave the distribution as Bernoulli. We can play with other things there, and you'll set the number of trees. Let's just set it 100. That's what it is by default. And I'll specify, I think the default shrinkage is 0.1, but I'll just specify just to remind you kind of what the important parameters are. Let's go back up here and look. Yeah, default is 0.1. So cool. That's kind of it's like well, it's not the same thing. It's kind of like a lasso or ridge regression kind of thing where you have to play around and figure out where that really parameter should be. Interaction depth, we'll leave at 1. Let's just move these down, which is the default. And we can actually set it to be verbose, so it's gonna tell us what it's doing when it fits. So here it goes. Quite quickly, we only have 100 iterations, 100 trees for fitting, so not that bad. This training deviance, so Bernoulli, we're not quite using the eta boost loss, we're using what's called the deviance, which is another loss, but this is the default one, so you can look up what that is. But notice that the only way to do this is with some kind of gradient boosting, and so this is kind of the loss. These are the tree number, and so you can see that this decreases, which is nice. That's what it should do, so we could say, look at the summary, and it gives us basically a variable importance. It's called relative influence, which is basically similar kind of random forest, but it's called variable influence. So again, exclamation, $, remove, free, lots of capital letters. These seem to be the ones that are important for predicting the class. And it gives us a little plot here, which is nice, of the variable importance. Or sorry, relative influence or variable influence. So that's nice. We can do predictions. Now you notice when I process my data, is, what do we call it? Is spam. This is numeric, and actually, so say type, is that how I want to do it? Oh, I guess it's called class. Right, this is an integer. So actually, but we're basically doing a classification problem. So GBM is a little quirky. It doesn't allow factors for that y. That's what it is. But so you actually want that your response variable in this case to be an integer, which is good because that's what spam base gives us. We can predict here. So you might run into errors if your y is a factor. It's going to give you issues. So you convert that to binary or something like that. Okay. There might actually be a multinomial. Well, or at least for binary classification, this is the way to do it. Okay. So we can predict from our model, and when we predict, we tell it how many trees. So for example, 100, I want to predict using all 100. You could predict using just the first 10, right? So you can basically truncate this wherever you want. and type I want response. This is going to give us our predicted probabilities. Okay, and so just like for logistic regression, I'm going to threshold these at 0.5, and this should give me my classes. So here are my predictions. And so I could look at, say, a confusion matrix, my training data, and it looks something like this, and you see, oh, we do quite well, right? The vast majority of these are correctly classified because most of our stuff is on this diagonal. We could look at kind of how this, as we add on trees to our boosted method, how the prediction works. So let's say we have our sequence of n trees is 1 to 100. And you can actually, instead of giving it just one value for n tree, you can give it a whole sequence, and it's going to give you a matrix. So this matrix has 100 columns because we have 100 different values, and it's going to give us number of rows here. It's going to be, so if you look at this, it's going to be about 2300, which is the size of our training data. And we can actually calculate the errors across all of our values for how many trees we want to include. We're just going to look at something like this. So this is going to tell us for our training data how well this works. So this is the misclassification rate for 1 tree, 2 trees, 3 trees, right? So I can plot this as such. Maybe something like that. So you can see our misclassification error rate. If I just include 1 or 2 trees, it does really bad because it's basically using a 1 split tree. Of course, it is horrible. It's like 35% error, right? But as I boost and I add more and more and more trees, you see that I'm pushing down, and pushing down, and pushing down my error rate. So eventually, after I push this all down, this ends up with a little above 0.05. Of course, we could do this for our testing data too. So let's just copy this out, and we could do this for our validation data. Because ultimately what we care about is the validation data. So something like this. So here, instead of predicting on our training data, we're going to predict on our validation data. So let's just add that in as an argument here. And now we want to do that. And let's plot away. And so we see that if we do this and we use about 100 trees, we get somewhere under 10% error. Now, not amazing. We could even, just for the kick of it, let's do this for both testing and training. So let's say that's test. And let's do this also for the training, just to see the difference, right? This is a classic example here. Let's say training, and then this should be testing. Okay. Whoa. Where did we run into? Oops, this should not be validate. This should be, oh no, that should be validate. This should not be though. Okay. And so you can see how, right, if we're, how our testing error basically always lives above our training error. Now, here we only fit 100 trees. Typically, in a kind of complicated problem like this, we could probably get some more performance if we play around with some of these other parameters here. We won't play with all of them, but let's just look at number of trees. So let's just add that on. So I could fit 1,000 trees. Let's do this. A little fancy move here. So let's do 1,000 trees, something like that. This will take a second to fit because now we're fitting quite a few trees. In fact, we probably want to turn off their verbosity here because we don't want to see all the output. Let's just rerun it real quick. And so you can see does a pretty good job of not overfitting too much here. But you see my error rate kind of flattens out around about, I don't know, 7%. You can see if I go too far down here, surely I'm going to overfit. I think we can fit 10,000 of these. I want to see if I can make it overfit. This might take a second though. But you can see in that previous plot that the test error did flatten out, but our training error was still descending. That is dangerous because you're getting to a place where you're potentially overfitting. And what eventually will happen, probably if you keep going and going and going, you could potentially run to a situation where you're overfitting. Now, for bagged methods like a random forest, are pretty hard to overfit, but you can overfit boosted methods. So you do have to be careful. So all of our caveats. Yeah. So here we see our training decreasing in the black there, and our testing actually is probably at its lowest point around here. So let's just maybe we can add these in. Let's actually pull off the plotting code here separately, and just plot this, and we can add in. Maybe we can add in some vertical lines. Something like that. Oh, let's give a color. Okay, even the plotting code takes a second. So you can see that our training error basically decreases, right? You actually don't hit a minimum at 10,000, but it's pretty close, and it's good as we keep increasing. We're basically you can drive this thing basically to zero. Way overfitting. And you can see that our best case for the test is somewhere around here, and so you can see it starts to creep back up, and we're overfitting, and this is a classic overfitting case. Just the couple minutes we have here, we can play this game. There are other tuning parameters we can play with. For example, so let's go back down to about 1,000 of these. If I change my shrinkage to be too high, so sometimes people call shrinkage, and you call them in neural nets. They're often called a learning rate. So a high learning rate means we don't shrink a lot, and you have a lot of ability to overfit, but you learn it faster. And so if you set this really low, you learn slowly. Let's set this really, really low, something like that. And if you set it too high, it's going to potentially overfit. So yeah, really low, basically, nothing gets added, right? We just start off with where we start off and you end your end, right? I don't learn anything. If I set my learning rate at something reasonable, default 0.1, now I have a reasonable curve. I'm still actually, I'm starting to worry about overfitting here. So you really would want to do some kind of nested cross-validation to choose these parameters. And if I set this at 1, good lord, what's this going to do? We're basically no shrinkage. Way overfitting, all right? Although actually my testing is actually going to cause issue, or my training actually overfits too, which is, that's hard to do. But so you want to play around with these parameters, but yeah, this would not be good. So if you weren't to look at these plots, the problem is they're somewhere in between where you won't notice it. Let's see if I can like say 0.5. No, that's not what I want. I want this to be about 0.5. Shrinkage should be about 0.5, so my learning rate. There's this, yeah. So here is the sweet spot of awfulness, right? Where if I would just look at my training data, right, I would say, oh, everything's going great. I need a bunch of trees, but my testing data actually only need about 100 here, right? And so I'm way over. I'm overfitting. I'm just overfitting now. It's pretty well protected, but you see it does creep up several percentage points over several thousand examples. So there's probably a sweet spot of awful here. We can hit where you won't notice in your training data, but your testing data, yeah, you'll notice something like that. And presumably with even the interaction depth also has the ability to kind of overfit. So let's see, let's put that at about 0.5. If I have a more complicated tree, this will take longer to fit because now I'm having a more complicated tree, so each of my baseline rates is more complicated. Yeah, look at that. Ooh, not good, right? So boosted methods, unfortunately, while people say they're great methods, and they are, you do have to be careful with choosing your parameters because they're not as kind of as baby proof as a random forest. Okay, but these are fun fun methods, and so this is a nice little introduction to these boosted methods.